When we talk about NMR spectroscopy and how it relates to all of the other forms of spectroscopy, there's a number of different ways we can do that. One of them is simply the transition that the light causes on our atoms or molecules. Gamma rays, for example, the highest energy form of spectroscopy that we typically will run across from time to time, basically takes the electrons and strips them completely off an atom or molecule. It's such an energetic technique. Whereas NMR spectroscopy, the lowest energy technique that we run across, basically just simply reorients the orientation of a magnetic nucleus in an external magnetic field. There are other ways of talking about spectroscopy involving the numbers, typically wavelengths, frequencies, or energies. Here are these various numbers all in common units. I'm using energy in kilojoules per mole. Those are the types of energy units that many chemists are most familiar with. And you can see here again comparing gamma to NMR as the two extremes on here, that gamma rays or gamma spectroscopy uses by far the shortest wavelength, highest energy, highest frequency light, and NMR over there is the lowest energy, longest wavelength, and lowest frequency light typically used in spectroscopy. There's another way of talking about it are the typical units, the units that spectroscopists who work carefully in each of these areas might use. For example, the X-ray and gamma ray spectroscopists often will talk about their spectra in terms of energy, either kilo or even mega electron volts. The UV vis spectroscopists and the IR spectroscopists will often use wavelength. We talk about the wave in UV vis, the wavelength of light that causes a transition in nanometers. The infrared spectroscopists studying molecular vibrations will also use wavelength, often a modified wavelength we call wave numbers or reciprocal centimeters. The microwave and the NMR spectroscopists will typically use frequency units. For example, our particular instrument is a 400 megahertz NMR spectrometer. Oftentimes there are modifications made to these units. For example, in NMR spectroscopy we will often, instead of using 400 megahertz and variations of that, we will use something called parts per million or ppm. The critical thing about comparing all of these is to realize that things like gamma spectroscopy and X-ray spectroscopy, these are sledgehammer techniques. These techniques have the highest energy and really make modifications for the molecules and the atoms that are being studied. NMR is a much lower energy technique. It's almost like tapping on your molecule with one of the most delicate little tiny hammers you can imagine. Being a low energy technique gives NMR some advantages and disadvantages. The advantage is it is likely the most information rich form of spectroscopy that we typically will do. The disadvantage, of course, is going to be that it's probably the least sensitive form of spectroscopy, in that we need relatively high sample sizes compared to some of the other types of spectroscopy to get the information that we are so interested in obtaining. The last bit to think about in comparing the various kinds of spectroscopy is simply learning how to convert between wavelengths, frequencies, and energies in all of these types of spectroscopy, just to get a feel or an understanding of the calculations involved in that. And that's the part we'll look at next.
All right, we're going to do a few of these calculations down here on the light board involving converting between units of wavelengths and frequencies, and then from frequencies into energy using standard chemistry energy units, and even doing a couple of conversions into other kinds of units as well, just to try to give an example of most of the calculations that you might run into, certainly in this class, and in any other spectroscopic type application that you might run into in the future. So what I'm going to do is do an example calculation involving light. It would have a wavelength of 640 nanometers. And I chose that simply because that's the wavelength of light here on a standard laser pointer. We've got a classic red light laser pointer. 640 nanometer light is what you're looking at. It's clearly, nice bright red light, easily visible. And what we're going to do is basically ask the question, convert 640 nanometers into frequency units, into energy units of kilojoules per mole, and into wave numbers. Okay, so this is what the question, just written out would look like. And so I have up here on the board as well the basic tools that you need to do any of these kinds of calculations. The classic energy of a photon equation, E equals h nu, Planck's constant and frequency. The classic speed of light equation that is used whenever wavelengths and frequencies have to be converted one into the other. And then the values of these three constants, our dear friend Planck's constant, 6.626 times 10 to the minus 34th joules seconds. The speed of light is 3.0 times 10 to the 8th meters per second. And every chemist's dearest friend, Avogadro's number, 6.02 times 10 to the 23rd, number of anything in 1 mole. So our first question, take 640 nanometers and figure out, question mark, what is the frequency of 640 nanometer light? The way you do that, you're going to use the speed of light equation. And we want the frequency, so no gigantic surprise here. I simply take the equation and solve it for frequency. Okay, nothing too terribly taxing here. And now it becomes basically a plug and chug problem, but with one provision. So I start plugging in my numbers. C, the symbol for the speed of light, 3.0 times 10 to the 8th meters per second. And if I just start plugging away, I would put in my wavelength, 640 nanometers. And when I do that, I do realize, I do have a problem. My units aren't matching up. I have meters on the top. I would have nanometers on the bottom. Simple problem, simple solution. Just turn 640 nanometers into meters. And that means I have to do a quick metric conversion, nanometers to meters. And remember, nano is billionth. I need a billion nanometers, that's 10 to the 9th, nanometers to equal 1 meter. You could also do that calculation from 1 nanometer is a billionth of a meter. Either way will work. And if you punch that out on your calculator, you should get 6.4 times 10 to the minus 7th meters, the wavelength in meters, and now my units match up very nicely, 6.4 times 10 to the minus 7th meters. And if I now punch that out on my calculator, and I do kind of make a little series of notes over here, I cheat so I don't have to actually sit here and punch them out. That comes out 4.7 times 10 to the 14th. And you'll notice the units, my meters cancel. I still have seconds, but they're reciprocal seconds, typically written this way. The other way you will see reciprocal seconds written is in units of hertz, okay, cycles per second. Either one is acceptable. I'm just going to use reciprocal leave it as reciprocal seconds here. There's the frequency. The red light laser, a photon from a red light laser is oscillating 4.7 times 10 to the 14th times frequency each second. That's quite a few. And so there's the wavelength frequency conversion. I'm going to apply the magic eraser to a little bit of this, and we'll move on to how much energy does this light supply. Now I've just simply written down our frequency, 4.7 times 10 to the 14th reciprocal seconds. Our next question is, what is the energy of this light in units of kilojoules per mole, question mark, kilojoules per mole. And I use that because that's a classic energy unit that we chemists use quite a bit in talking about energy for our molecules. So that's the one I'm going to aim for. And since it's an energy question, yes indeed, the energy equation is now going to play a role. I've already got the frequency calculated. That's convenient. Now I simply need Planck's constant. And so just a plug and chug again, 6.626 times 10 to the negative 34th joules times seconds. Oh, you never get tired of saying that. Times 4.7 times 10 to the 14th reciprocal seconds. If you look at those numbers here, man, your scientific notation button on your calculator is just going to have a grand old time with this one. You also notice, kind of conveniently, I have seconds and reciprocal seconds. My second units are going to cancel, leaving me only joules, which is kind of convenient because that is exactly what I was trying to calculate here. And if you punch this out on your calculator, I got 3.1 times 10 to the negative 19th joules. That tells me that 1 photon of light from the red light laser doesn't generate, has very little energy in it. But of course, we're usually not interested in how much energy 1 photon has. We're interested in, large quantities of these things that we usually interact with. So I want the energy units in kilojoules per mole. I've got the joules. And so now I'm going to go ahead and turn that into joules per mole. And of course, that's a simple calculation. Just take the number times 10 to the minus 19th and multiply it by our dear friend Avogadro's number, 6.02 times 10 to the 23rd. Make that a good 23rd. Number of anything in 1 mole. More fun scientific notation for your calculator to just have all kinds of fun with. If you punch that one out on your calculator, I came out with 186,977, and that's joules per mole. And of course, that's just one tiny jump away from, and just rounding off to 3 digits, 187 kilojoules per mole. Okay? So 1 mole of red light from the red light laser would, has 187 kilojoules of energy in it. And so there's a classic energy calculation, how you can turn energy of light either expressed as joules, kilojoules per mole, or some combination like that, and turn it back into frequency, or frequency here into energy. The last one is to do the calculation with wave numbers. So again, a little bit more magic eraser, and we'll put that one up here. The last one is to express this frequency and this wavelength in a more traditional IR unit, reciprocal centimeters, cm-1, which is also known as wave numbers. Each type of spectroscopy usually has its own set of units, ways of looking at it, but they are all interconvertible. And so I just wanted to show that by taking a visible light frequency and wavelength here and expressing it in units that are more commonly used in either microwave or infrared spectroscopy. So, aiming for reciprocal centimeters, what I'm going to do is take my wavelength, and I had it earlier up here on the board in terms of meters. It was 6.4 times 10 to the minus 7th meters, okay? And that is simply converted into centimeters, and then you're just going to take the reciprocal of it. These calculations are not that difficult to do. And so, yes, good old meters to centimeters, okay? And of course, we remember that 1 meter is 100 centimeters. We do all remember that. That's good. And so that is just going to be 6.4 times 10 to the minus 5th centimeters. And then, of course, reciprocal centimeters, wave numbers, is simply the reciprocal of that number. 1 over 6.4 times 10 to the negative 5th centimeters gets me, and I punch that out of my calculator, I got 15,625 reciprocal centimeters, or 15,625 wave numbers. If you remember standard infrared spectroscopy, on a standard spectrum, it usually runs from about 4,000 down to somewhere in the neighborhood of 600 wave numbers. You can see we're quite a ways outside the standard infrared spectroscopy range. Indeed, we are outside the IR and now into the visible light, but like I say, any of these frequencies, energies, wavelengths can be converted one into the other from any type of spectroscopy, and it just helps to kind of anchor us from types of spectroscopy we may be more familiar with, like infrared, and just be able to convert all these numbers from what we use in NMR spectroscopy to all the other units in all the other forms of spectroscopy. So take that into consideration, practice those a couple of times, and we'll see you later.